optimized Genesis sequence.
All right. Hello, everybody. Welcome to this talk where I and Roy would like to talk about a viral coding challenge which happened earlier this year, the 1 billion row challenge. And what it's about, it's almost kind of already in the name. I'm Gunnar. I work with a company called Decodable, and usually I do this talk alone by myself, but today it's, I think, the first and probably last time I'm ever going to do it together with Roy. How about you introduce yourself?
Yeah, so my name is Roy van Rijn. I work for OpenValue, a Dutch IT company, and I got nerd sniped.
Pretty hard.
Yeah.
Awesome.
Very hard.
Roy played a very special role in the challenge, and we will touch on that later on. So that's why I'm so excited to have the opportunity today to have this talk together with him. And over the next 50 minutes, I would like to, or we would like to take you on this journey, which started with this tweet and a blog post I put out on January 1st this year, and this motivated the challenge. And I will explain, of course, what this was about in detail. And then it quite quickly evolved. People started to participate. People started to solve the challenge in Java, but then also in all kinds of other tools and languages and platforms. People started to write articles.
Let's do a show of hands. Who here has heard about the contest?
Who has heard about it? That's very good. That's
good.
Half of you, maybe. So who has participated? Yes, a few people. Very good, awesome. I heard some of you were doing really well. Very good, great.
No spoilers, no spoilers.
No spoilers, but let's see. Right, so people did it. They wrote about it. There was the article in InfoQ, most read article for the first 6 months of the year. There was this guy, Prime. I had no idea who he is, but apparently he's like a famous YouTuber. He also covered it, and it really kind of blew off. And then, I wanted to give everybody a personal certificate of achievement, so I learned how to create 160-something PDFs using the Mac Milmer thing. You still have yours, I guess?
Yeah.
And I also sent T-shirts and coffee mugs to the people most successful in the challenge, apart from Roy, because he didn't want to have any swag, so he didn't get
I've got too much swag already. It's not good for the environment.
Right. I think some people here have the T-shirt, actually. All right, so what was the idea there? Why was there this challenge? Well, I thought it was between Christmas and New Year's Eve last year, and I felt, how about doing something to learn something new? And I mean, there's all those new Java versions coming out every 6 months, right? And they come with new APIs, new features, and it's really hard to keep track of that and know what's new in the platform. And I thought it would be interesting to apply that to some sort of practical problem, to take those new versions, new APIs, to see what we can do with them. So learning something new, that's definitely the goal. Also having some fun, always good. Then, of course, and again, coming back to Roy, inspire others to do the same, right? So the Java community, I think, is a pretty healthy, active, diverse community, and doing this sort of thing, it inspires everybody to come together and have some fun.
What I really liked is that everything's open. Like,
right.
Most challenges, you submit something, and at the end, you see who's won. And
exactly.
In this case, from day one, everything was open source. Like, you could just steal my code, you could steal Thomas' code.
Right.
Nobody did that. Well, we borrowed ideas, and we learned a lot of new stuff.
You could take inspiration.
And that's probably why it was successful, because people could see everything evolve, learn from each other, and that was really fun.
Absolutely. And then there's this thing, right? And I mean, I would say it's a myth from the past, but sometimes people still have this misconception: Java is slow, and they have some doubts about it. And this is also what I wanted to help to debunk, right? And I think, as we will see later on, the results definitely it couldn't be any further from the truth. So then let's dive a little bit into what was the challenge, what was this about? And it's pretty much all in this nice visual here. So the task was, you have a file with temperature measurement values. And it's kind of like a CSV file, only that the separator is a semicolon, not a comma, but kind of like a CSV file. And 2 columns, just a station name, so something like Hamburg or Antwerp, Berlin, and so on, and then a temperature measurement, kind of randomized value. So you had those 2 columns. And now the task was simple: aggregate the contents of that file, and for each of those stations, Hamburg, Antwerp, and so on, calculate the minimum temperature value, the maximum temperature value, and the average temperature value. The only caveat was, this file, as it is in the name of the challenge, has 1 billion rows. So it's quite sizable. And if you have that file, it's like 30 gigabytes of size, a bit more. So, not a trivial amount of data. And then you had to put out the result, and you kind of see already it's like this weird 2-string representation from the Java hash map implementation. didn't really think much about it. And actually, some people who solved it using relational tools like Postgres and so on, they went to great lengths to produce that output format, which kind of was just randomly chosen. So kudos for people who did that. In terms of the rules, well, I said it is a Java challenge, right? And I'm part of the Java community. It's what I want to help to evangelize. So that was the idea. It's a Java-only thing. And also, just frankly speaking, I didn't want to bother setting up a Rust tool chain, C compilers, and so on, just to make my life a bit simpler. But then, of course, people came and also solved the challenge in other platforms, other languages. And they could do it. They just couldn't officially be part of the challenge. Very importantly, as we will see later on, you could use any Java version. I used the SDKman tool, by the way. Who's using SDKman? That's not enough. All the other people, you also need to use SDKman because it really makes it very simple to go back and forth between different versions, install them. So definitely try this out. It's what we use in the challenge to work with all the different JDKs because they come with different garbage collectors, different preview APIs. In the case of GraalVM, the support for native images. So that's what we use for going back.
It's just a single line for each switch.
Exactly.
It's just a single line. That's perfect.
And then you have it. Exactly right. No dependencies. I mean, you could just get to go to Maven Central, load some library, and parse the file, but where would be the fun in that, right? So you were supposed to solve the task by yourself. You want to learn something, going back to the motivation. And as Roy said, copying was allowed, right? So you could go and take a look at other people's implementations. You shouldn't, of course, just take Roy's implementation and say, hey, that's mine. That wouldn't make much sense.
Not if you want to win.
No, nobody did that, I think. Nobody took yours anyways.
Exactly. Exactly.
It's getting more intense. But yeah, so people took inspiration, they took up the tricks from the other people, and then in some cases even teamed up and put in a joint submission. I ran all this on one machine because, well, it has to be comparable, right? So and actually my employer, Decodable, spent a bit of money to hire this nice box on the Hetzner cloud. Big kudos to them. 32 cores, out of which I only used 8 cores. Later on, I will explain why only 8 cores. Quite a bit of memory. The reason there, and actually the file was loaded from RAM disk, the reason was, well, we don't want to make this about I.O. So we wanted to have I.O. not be a part of the equation. And then I did 5 runs of each entry, discarded the fastest and the slowest one, and then from the remaining 3 runs, I took the average, and this was like the result for a particular implementation. That's how we ran it. Now, let's talk a little bit about how people did that. And this is, I guess like I'm a regular Java developer, so this was like the code I came up with, and I provided that as a baseline implementation so people could see what the program is supposed to do. And you can see it here. This is using the Java Streams API. I would argue pretty canonical Java code. So what's happening there is, well, we use the Streams API. We use this files lines method, which gives us a stream with all the lines of a file. Pretty easy to read that. And then for each line, we want to map that line. In that case, we just split the line at the separator, at the semicolon. We create this sort of measurement object which keeps track of the name and the value. And then, well, we want to aggregate those values, right? And this is where this collector comes in. So this is what we use to group and aggregate the values. So what we need to do is, well, if we get a new line, we need to add it to the aggregator object for that row. So let's say we get the second value for Hamburg, then we want to put the values into that aggregator, right? So we wanted to keep track of the min value, the max value, and for calculating the average, I keep track of the sum and the count, so that later on I can divide sum by count for the average. Next thing, well, if this runs concurrently, well, I need to merge multiple aggregators, and again, I just propagate min and max and sum and count. And finally, when I'm done with that, I need to emit a row for each of my weather stations where I just propagate the min value, the max value, and then, for the average, I divide sum by count. So I would say pretty canonical Java code. I don't know, took me like half an hour or so to write. Guess I did some mistakes. And this then ran within close to 5 minutes. And I would say, if you do this once off for 13 gigabytes of input, it's not too bad. But of course, it's not good enough for this sort of challenge. And you want to be a bit faster than that, right? And this is what we want to talk about, how you can do it. And now this is where Roy comes in, because, well, if you do this sort of challenge, it could go just unnoticed. Nobody cares about it, right? And that would be pretty embarrassing. But thankfully, Roy stepped up, and he really quickly, within 2 hours or so, I think, he submitted a first contribution, which just was a little bit faster. And the idea was just, well, to show others in the community, to inspire them, this is something cool. This is something you and I and we all can participate in. So big shout out to Roy for doing that.
Even the manager.
And yes. And so then let's dive a little bit into some of the techniques for making this a bit faster than 5 minutes, right?
Yeah.
Take it away.
Yeah. So the first real change I did was pretty impressive. It was because this machine has 8 cores, and we're currently only using 1 because we're reading all the lines and we're processing them on a single core. That's not very fast. So what I did was I added .parallel.
Great job, man.
Yeah. Thank you. And you can see this already almost 8 times faster, right? Instant. And it's very cool that we can actually do this. Like 10 years ago in Java, you weren't able to do this. If you wanted to do something like this, you would need to spawn a couple of threads and divide the work and other stuff. Just 1 word. That's pretty impressive, I think.
That's pretty good value for money, I would say.
Yeah. But now comes even more interesting, because who knows about this gem? It's currently in the latest Java versions. Basically, it allows you to have faster access to foreign memory. Let's look at an example. So if you open a file, you can use a file channel .open. You give it a path name, and then you can basically say, I want to read this, and now the operating system takes care of actually loading it in memory. You get a memory segment or a byte buffer, either way, and basically you can access the objects or the file as if it was in memory. You don't have to worry about having a buffered reader, etc., etc. This is just as if it was in memory and you can access it. And this is very fast because you can delegate everything. You can delegate the reading to the operating system, which is optimized, of course, to do that. And even if the file is very large, so in this contest, the file was 13 gigabytes, and even if you have less memory than that, it should be fine. Like, the operating system will map it for you. It doesn't have to fit instantly in memory. It will take care of that, which is really cool.
Right. And we should say, well, this is relevant because if you just have this basic parallel call, it will, not take fully advantage of all the calls. Like in parts of the I/O, this still happens kind of sequentially. And if we do what we are going to see here, like really fully parallelizing the reading path, then we actually take advantage of all the 8 cores.
Exactly, because adding .parallel means that the processing is done in parallel, but the reading itself is not. Turns out that this was actually one of the next things people started to do, was break the file up in multiple pieces. So we look at the amount of available processors, so in this case, 8 different cores. Then we get this file, and we in this case, random access file, because we only need to read. We break it up into 8 different chunks, and each thread will be able to basically process this and output a result, parallelizing even the reading part. This is, again, a big speed up.
Absolutely, yes. And what actually then people in the end did, they didn't split up into 8 chunks. They split it up into much smaller chunks. And in the end, it actually went down to 2 megabytes. And the idea was, well, one of those 8 threads, it will always be like the last, right? Because just in terms of how like the workload is distributed and so on. So still all the other 7 ones, they have to wait for the last one. And if you split up the work in much smaller chunks, and then we have sort of a backlog of tasks which we can go to, and then whenever a thread is done, can fetch the next chunk from there. We just like spread out the workload.
And that's just one of the advantages. There are multiple, because if you start reading it sequentially and dividing, like, then the memory map file will just load a part of it in memory, and then you're processing that with 8 different cores sequentially in 2 megabyte pieces. And also it helps if the CPU caches are around 2 megabytes, then it just loads that into the L2 cache and L1 cache, and it's done only once, and then you parse that entire thing. So it helps in multiple ways to know your architecture.
Exactly. Yep. All right, so Challenge ran, was the first week of January. People like Roy and others came and put in their submissions. And then, of course, whenever there's this sort of thing, you have some sort of conspiracy theories, right? So one of them was, well, this was actually a problem which you had at your work at Decodable, and you couldn't solve it. So you farmed it out to the community for them to solve it for you. And I can tell you, this would have been the most stupid way for me to solve that, because I didn't do anything besides running that during the entire month of January. So, I put way much more time into that had I just done it myself. So no. Is it a hidden ad for GraalVM? We have like folks from the GraalVM team here. No, it was just that the workload lent itself very well towards being solved with GraalVM. And for, naturally then people... people did that. Is it an ad for Epic, the CPU this was running on? Again, no. So, people come up with all kinds of ideas. And then the other thing is, I spend too much time on Hacker News. I guess other people do as well. And there was this guy, and it's already like grayed out, right? Indicating people don't like the comment. But what it says is, this is like a trivial problem, and like everybody who can program just a little bit, they will have solved this in like 2 hours. And then, so there's that guy, and then you have like all the people from the Java community, like, people from the GraalVM team, Alexei Shipilev, Cliff Click, like one of the OGs from the Java ecosystem to begin with. Like all those people came together, and they spent the entire month of January. But sure, there's like the random guy in Hacker News who would do it in two hours, right? So kind of funny to see the different reactions which this sort of thing triggers. So then let's talk a little bit about parsing. So we spoke about taking advantage of all our CPU cores, making the most out of what we have. But of course, what is it we actually do? We need to process those lines. And I will start with just a little bit, because again, that's code what I guess I would be able to write. So it's a basic state machine. Instead of using like the regex to split the lines, which isn't very efficient, obviously, here the idea is, well, just process those byte buffers which we have, process them one by one, and have a simple state machine which then tells us what to do. So this is what we are doing here. We fetch the next byte from our buffer, and then, well, depending on whether we are before or after the semicolon, we either are in the state that we read the characters which form the station name, or we are in the state to read the characters which form the measurement value. So that's what's happening here. And depending on that, we feed the next byte into some sort of builder object, for the sake of the example, to accumulate those bytes until we have seen the end of the line, right? If we have seen the end of the line character, then it's time to take those two builder objects and feed them into our aggregation engine. So that's what's happening here is we assemble a string with the station name, for the sake of the example. We find out our numeric value, and then we aggregate it. So let's dive a little bit into this bytes to int method, because this is interesting. Because, well, when I started to run this challenge, I would not expect how much people would take advantage of every little detail they could. And now in this case, well, as I mentioned, this file had 13 gigabytes of size, so there was just not a good way I could go and upload this to GitHub and share it with people. So instead, there was a data generator, and people had to run this generator locally to create that file. And now this generator just happened to only produce values which had one fractional digit. So like 2.9, 8.7, but no more than one fractional digit. So people realized, well, instead of having to do floating point arithmetics, what we also can do is we can just, game a little bit the system and do actually integer mathematics, which are much faster, of course. So this is what they did. They, considered the values as an integer. So instead of, 10.1, they would consider the value as 101, and then they would, in the end, they would divide it by 10, just at the final output phase. So that's what's being done here, reading those bytes, assembling our integer value. And now this gets us down to 20 seconds. Already one order of magnitude faster than the initial baseline, right? Again, pretty good, I would say. You may stop here for most purposes, but then again, if you want to do this really fast and see how fast you can go, you want to do some more, right? And this is where this SIMD API comes in.
Yeah, so there are multiple ways to make this even faster. The bottleneck now becomes that if you want to work with per byte basis, it's really slow. You do 1 byte at a time. What if you can do multiple bytes at a time? Parallelize that. You can do that in multiple ways. So one of the ways is to use the new vector API. This is, at the time it was still an incubator.
It still is.
It is still an
like
incubator.
Like in the 8th or 9th or 10th, whatever.
Basically, this allows you to create a vector, with bytes and do an operation on that. Basically, you can, for example, find the separator in 8 bytes or even larger vectors in a single go. And your operating system will take care of that. This is really fast.
And what's interesting on that one is, before we had this vector API, we as Java developers, we couldn't really use those SIMD instructions, right? So in some cases, the compiler would auto-vectorize code. So under the hood, it would compile down to those instructions. But as application developers, we had no means of doing that. Whereas if you wanted to do that, you would have to do C or Rust, I guess, like a language a bit more closer to the machine level. But now with the vector API, we actually can do it. And I would argue suddenly we are even in a better spot, because what happens here is that the compiler, the Java compiler, will compile this down into the specific machine instruction set which we are running on. So it could compile down to Intel code, it could compile down into ARM, like Neon instructions, which means, we can make use of vectorized computations and still be portable. Whereas if you were to do this with like the native code, you would have to do it specifically for machine, right? And I just find it interesting, like in Java, first we were a little bit behind when it came to that, and now suddenly I think we're like in a really, really good spot, right?
Yeah, it's fun to see that the guy who came in 4th in the competition, I think,
right,
he was using OpenJDK for this reason, so he could use these vector operations. All the other entries, on the other hand, were using Grau. Grau didn't support this vectorization, so we needed to do some tricks by hand. And one of the tricks is showcased here. This is Java. Doesn't look like Java, but this is Java. Basically, what you can do with some bit shifting tricks is that you can do the same thing as we did before. So you load multiple bytes of a string into a long value and do some operations on that. For example, find a separator. In this case, we make a mask for the delimiter. There are some lowest set bits and highest set bits. You do some math, and without any branches, out comes basically your result. Where is the separator if it's in the code? If you really want to know how this works and the absolute specifics, and we did a deep dive on Thursday on Tuesday together with Thomas. It's already online, 3 hours long, all technical details.
Right. And just going back to this code here, what we see, something is missing here. Does somebody realize what's not on this in this code? There's no conditionals. There's no branching there, right? So essentially, all this code just will be executed sequentially. And this is very beneficial for our purposes if we remember how CPUs are actually going to execute the code. And the way it works essentially, like each instruction has like those 4 phases: fetch, decode, execute, and then the result will be written back. And now the interesting thing is a CPU will take multiple instructions and execute them at the same time. So while we decode our one instruction, we already can go and fetch the next one, and so on. So we have like multiple instructions in parallel in our pipeline. And now for this, of course, to work, we need to know what this next instruction is going to be, right? So otherwise, well, we cannot go and fetch it. And this is why this branchless code is so useful, because, well, then it's always clear what is the next instruction, right? Whereas if you have like conditionals, if else, then there's what's called the branch predictor. So this will try and make an educated guess based on like the past and all kinds of smart reasoning, what could be the next instruction, and we will then take and fetch that one. But of course, this prediction could be wrong, right? And in that case, if we actually take that if the other way around, then we would have to flush this pipeline and start all over. So then the code would be would be much slower. And this is why having no branches here, that makes this very, very fast. And now, if you really, well, you would like to learn more about it, you can go to the talk from Roy and Thomas, and you also can buy this book. So I bought this book during the challenge. I didn't know about it. I learned about it. And this has all those bit level tricks. So definitely go and check this out.
The thing is, hopefully, when the vector API is like fully finalized, you don't need these tricks anymore. Well, or you can use the vector API.
Yeah, I guess people will still do it and try and make it even faster.
Absolutely.
All right, so again, challenge was running, I don't know, 1 week in, 2 weeks in, something like that. People submitted their PRs, pull requests with their new implementation. I would wake up overnight, let's say 10 pull requests would come in, I would go and run them on that machine. And then at one day, something was off. So I was taking the next implementations, and suddenly the results were bit too fast. It was like twice as fast as before. So I, took one which I had evaluated before. It was much faster than before. Well, what happened is, well, I had, I thought I would know what I do, but of course I did not know what I do. So I got a machine which had dedicated virtual cores. It was a VM, but the cores were dedicated to my workload. So I thought, okay, I should be safe. No, like noisy neighbors. Nobody is competing with my workload there. It was true, but then still, well, it was a VM, which meant people at the Hetzner cloud, they moved at some point this workload to another host, which was just more capable. I don't know why, maybe it was random, maybe they saw there was lots of load on that machine, let's do like a favor to the guy and move it to another machine, I don't know. But in any case, I had to, I had a bit of a problem. I had to like reevaluate everything. And now the good thing is the wonders of the Java community happened because, well, I sent out, like my little call for help. Guys, I don't know, what should I do? And well, first of all, again, my employer, Decodable, they agreed to sponsor and pay for like a dedicated machine, so shout out to them. But then also, I'm not a big Linux sysadmin person. I know a little bit, but not enough for configuring a machine to make it like, suitable for the purposes here. So I asked for help, and then thankfully Rene, which I think sits over there, so he replied, so hey, I can help you with that. And the funny thing was, well, we didn't know each other. We just had a phone call, and I had a good feeling about him. And then I said, okay, give me your SSH key. I will upload it to the machine so you can connect and do your thing. Don't run your Bitcoin miner. Thankfully, he didn't. And I just found it amazing how the Java... Was that?
Or did he?
Or maybe he did. Yeah, I don't know. Did you? I don't know. I just found it amazing how the community in Java comes together to help with managing the machine, but then also all kinds of other things. So initially, the problem wasn't like super well defined. And of course, people had all those kinds of questions. How long can a station name be? What kinds of UTF code plane characters could there be? What's the range for the... I think I had defined it. But, they wanted to define and get answers to what are the constraints of the problem. And people then again stepped up and built a TCK, like a test compatibility kit. Because
it also helped you, right? Running the contest, instead of evaluating every pull request, you can use the test set.
Right, yes, of course. But because you don't only want to be fast, first and foremost, you want to be correct, right? So yes. You need to pass this TCK. So we had that. You can see it here, like, a bit of like expected values, and you get the gist of it, right? And also, just running the thing was a challenge because, well, you want to make sure like the environment is set up correctly, like you use the right JDK, all the settings are correct, this TCK needs to be invoked. So there was a bit of shell scripting involved, and Jason here, he did a great job of just implementing shell scripts, to make this like very easy to use. So big shout out to him. And I would recommend, if you are into shell scripting, I guess you all love shell scripting, check out the scripts in the repo to see what you can do there. All right, so then I think we want to talk a little bit about bookkeeping, right?
Yeah, so we talked about the file I/O, we talked about parsing all the records, but we also need to store everything because we need like the output, the result, right? And to do that, initially we used a hash map. So short session. How does a hash map work? Basically, this is a hash map of size 6. Let's keep it simple. We are adding Antwerp here. There's a string, we generate a hash code, which is just an integer, just a number. We do modulo the size of our hash map. In this case, we get result 1. Now, that's where we put it, and that's where we know where to find it. Now, what happens if we add another city, Hamburg in this case, again, integer hash code, modulo operation, we end up at the same spot. It's not ideal, but we can solve that. So what does OpenJDK or the JDK do? It starts to create a tree structure. So basically, it adds the objects in series or in a tree. And if you now try to insert Hamburg again, for example, you get the same hash code. You first see Antwerp, and then you say, well, I have to traverse the tree until I find the record that I'm actually looking for. And if a hash map becomes too crowded, you can just scale it up, and then you just recalculate all the hash codes, and you can rebalance everything. We don't want that, because there's an issue with this. Actually, two things. So we don't want to rescale everything. So ideally, we want a fixed set, and we want to use that. And also, ideally, you don't want this nested structure, because that's not really fast and pleasant in code. So I turned to ChatGPT and I said, well, how can we actually solve this? And he told me, I don't know.
That's a good question.
Just take an array and use that. And if you have a collision, instead of creating this tree structure, just put it in the next spot. This is called forward probing. I had never heard about this. Just put it in the next spot. And this just works. I never considered this. If you now try to insert Hamburg again, you'll see the entry on this spot isn't the one you're looking for. Then also you move to the next one, and it's there. And this works really surprisingly well, and this is very fast. And you don't even have to do the next one. You can do larger steps, so 30 in the future. No, this just works. It's really cool. So how do you implement this? This is how. We have this hash code, and we instead of doing a modulo operation, which is really slow, we do an AND operation because we're using a size which is power of 2, even faster. Then we get the entry there. If there is an entry there, we either update it or basically we update it. And if nothing is found, we just do index ++ and we go to the next one. If nothing's found, we can insert it. And that's it. This is our entire hash map. Perfect.
Yeah. And the important thing there is, it comes back a bit to this idea of people, really optimizing for the particular data set. Because what you want to do is you want to avoid this case here that you hit an existing entry as much as possible, right? Because then you have to do like this slow thing and actually compare the name of your incoming value with the name which is at this particular element in your array. So that's what you want to avoid. And what people did as well, they used hash functions which were optimized just for that data set from this data generator, which then would be like collision free, and it would make the implementation just very fast for this particular data set. And I felt this was a bit
because there were only
400 something. You're right. Yes.
Station names in the challenge, so it was pretty easy to come up with a unique code.
Exactly right, and it was a little bit not what I had in mind. And also people solved this in a more generic way. So in the end, we did multiple result boards, and we will see how people did differently. Now the thing is with the hash map. Well, again, I had no idea people would implement their custom map structure, so I learned it. Now the problem is I also created lots of work with that for myself, because the problem is you cannot have a test which would prove the absence of any sort of hash collision, right? It's just not possible. And sometimes it would happen. People would have an implementation which is very fast. And then I realized, it's fast because they don't deal with this collision case, which obviously makes it faster, right? So, and then in the pull request template, I added the question. So if you are using a custom map, then please point me to the code where you deal with hash collisions. And that's what you see here. So, hey, anonymous person, where are you dealing with hash collisions? No, I didn't do it, so that's why it was that fast. So, a bit of a problem I created for myself. But most of the people were very understanding, and then would sort out this issue very quickly.
Yeah, so like I mentioned before, most people were using the GraalVM here, and especially the native image compilation. So what you can do, if you've got a Java program, you can do a native image, which basically turns it into a binary you can just run. There is a JVM running, but it's now a native image. So we were using a lot of options, and one of the cool things that we added was the GC, the garbage collector. Who knows what the epsilon garbage collector does? Okay, what does it do? Nothing, exactly. This garbage collector does nothing, and it works. In this case, we know exactly what we're doing. We don't go over memory limits. We just let it run, and we terminate the application. Question?
Right, yes, of course, you need to allocate, but then you don't need to go and check whether you can free.
Yeah, and it's way faster because it doesn't have to put in the read boundaries, for example.
Right. So yes, this was one of the interesting takeaways, and I guess this could be applicable for you if you, let's say, work on a short-lived program like a CLI tool, or you just get away with allocating just at the startup of your application, and then don't do it again. So that could be interesting. But also what I found interesting, so yes, GraalVM lets us build those native images, and they are in particular fast to start up because there's no JIT compilation involved. So this is why it was so useful for the problem here. Because people went down to such low numbers that actually saving like 200 milliseconds upon startup would make a significant difference. But the very interesting thing is, and everybody I would recommend, when you're at home, go and try it out yourself. You also can use GraalVM as a JDK distribution, and you can use the GraalVM compiler as a replacement for the C2 just-in-time compiler. And now I'm not saying, and I guess Thomas would disagree, but I'm not saying that it is faster for every workload, but it is faster for this particular workload. And it just is a means of one simple configuration, right? Just go to SDKman and say, hey, I want to use GraalVM as my JDK distribution. And then you can see, does it make a difference for your workload or does it not? So in this case, I think it just would shave like 5% off essentially for free. So definitely I found that's very valuable insight, and I would very much recommend everybody to give this a try. Do you want to talk about this nesting trick?
Yeah, so there were a lot of tricks that people started using. One of the things that Thomas noticed is if you do this memory mapped file, when your program stops, the operating system still needs to unmap it. And it sounds like this could be very fast, but what it actually does is that it's overriding all these parts of memory because it doesn't want to leak any secrets. So this is actually a very slow thing, and Thomas started to measure this, and this was like 20% of his runtime was the kernel unmapping the file. So what he did, just spawned two processes. One is for the challenge, and one is just doing the actual calculation. Once the calculation is done, the challenge process just stops. Hyperfine, the tool we use to measure everything, stops, and then the kernel starts unmapping in the background, but we don't care about that. Right. You allowed this?
Right, yeah, I felt it is in the spirit, right? Because, I mean, you could say it's like a trick, but then I felt, okay, it's also something which I think some browsers, for instance, do in some cases. So I felt if it helps to solve that actual problem faster, which is like printing out the right result, then why not, right? Let's allow it.
I'd never used unsafe before, and I started using this, and my code literally turned into C. Which is really cool, but it saves time, right? Even we have some alternatives, and even the best alternatives, like memory segment and byte buffers, they still do a lot of checks because safety is good. Like in every other application, you want safety. You don't want to write outside byte buffers. You don't want to be able to read outside byte buffers. That's a good thing, but not for this because we want ultimate speed, no checks, just raw, unsafe.
Yeah, and then the one which I found interesting is this listing here on the right side. And this is, if you look closely, well, we have the same sort of processing loop 3 times there, right? And you might wonder, well, that's weird, right? Because, well, this is like written down in a sequential way, so it should be executed sequentially. So why is there any point in like repeating ourselves? And the reason is, well, actually, our CPUs, they have multiple execution units, so still, the compiler will be able to recognize there is no data dependency between those loops because they work on separate chunks of our input data. So actually, this can still be executed concurrently. Now, why is it 3 times? It's just like empirically determined on that machine, like, repeating it 3 times, that was the fastest. And now, well, I guess this gives you a bit of an idea that, well, we start to have some sort of questions around maintainability of that, right? Because I already see it like the new guy, probably I would be like the new guy coming onto the team, and I see this is the same code like 3 times. Let me go and refactor it. Let me like make one loop. We don't want to have it repeated, right? And boom, our optimization is out of the window. So you probably would want to put a comment there, or maybe you just wouldn't want to do it if you don't really have this sort of task to solve. Speaking of the results, let's talk a little bit about the results. So as I mentioned, I ran this on 8 cores, and the reason was, well, my initial environment, like this virtual one, this had 8 cores, and then when I moved over to the dedicated server, I kind of wanted to stay in the same ballpark. That's why I used 8 cores, and that was like the official, evaluation. And the fastest one was 1.5 seconds, as we see here. So from Thomas and colleagues from the GraalVM team. This was with 8 cores. Then, of course, we wanted to see, well, we have those 32 cores, and we do have hyper-threading, so let's see how fast we actually can go. And now this brings us down to 300 milliseconds. And I think, well, for Java, for any language really, being able to process 13 gigabytes of data within 300 milliseconds, I mean, sure, it's a beefy server, but I don't know, I find this very impressive. So that's all the cores. And then, well, I mentioned people optimized a lot for that particular key set, right? So those 400 something station names from this data generator. And I felt it's not what I really had in mind, but I also didn't want to change the rules after the fact, so it was fine. Let's go with those 400 station names. But then also, there was other school of thought who said, okay, we want to solve the problem in a generic way. We don't want to make any assumptions about this data set. And that's why we had like another evaluation with 10,000 random station names of all kinds of lengths. And as you see now, this leaderboard is mixed up, right? So
there's one name missing here. Like Thomas completely disappeared from this
right,
list.
so yeah, Thomas is not here anymore, right? And other guys are here.
And that's actually, he talked about it during the deep dive. There's a good reason, because if you look at the original data set,
right.
You look at the distribution of the names, almost 50% of it has a city name of 8 bytes in length, or
right.
up to 8 bytes. There's like 49% which has 8 bytes to 16 bytes, and there are a couple that are longer, but it's neglectable. So he basically optimized everything for those two.
Right.
And this data set had city names up to length 100.
Right.
Yeah, and then it doesn't work.
Different leaderboard, and still I would say very impressive to solve that within 3 seconds.
Absolutely.
Now, to get there, well, it was like really a long effort, right? So as I mentioned, it ran for the entire month of January, and people were free to iterate on their implementation. Some did it more, some did it less. So here in this case, it was again for Thomas. I'm not sure why you are so many times here, but it was like 10 PRs or so to iterate on that. And what I found interesting, so this is from Roy. So he did a great job in documenting his journey. So you see like what he did and what it yielded in terms of the outcome. And what I in particular like somewhere down here, it starts to get slower again. Right, thanks. It starts to get slower again. And this is, well, because at this sort of level, it really depends on the specific CPU, and it's even the generation of the CPU. And now, I think you had an ARM MacBook, right? So doing things which are faster on the ARM MacBook actually made it slower on the Intel evaluation machine.
The last 2 weeks for me were very frustrating, because every day, it's like I changed the code, and I was the fastest entry on my own MacBook, like by far. And then I submitted, and you said, well, it's slower.
Right.
How?
Yeah, and I think you found like an old MacBook somewhere in your closet,
exactly,
right? And like
exactly, and that was an x86 MacBook, which is more similar to the server, and I could actually, things started to correlate a little bit more, but still not very much.
Right. And yeah, to me, I don't know, as a Java developer, you don't really tend to think about those kinds of things, right?
So
but here for those challenges, well,
basically in the last week I knew the only way I could improve and maybe take a chance on winning the tournament was actually to rent a server.
Right.
But I'm Dutch, so I'm not renting a server for a contest.
Now, of course, the big question is, should you do any of this? And of course, I wouldn't be a good software developer if my answer would not be, it depends. So, I mean, if you work on like your regular standard e-commerce application, probably you wouldn't do it, right? So you would just do like the simple thing to just avoid like the stupid mistakes. Don't allocate objects left and right. For instance, there's this implementation here, which check out the QR code, which I really like, because this runs in like 20 seconds, so 1 order of magnitude faster than my initial baseline, and still it's very well-readable code, I would argue. You can understand it, you can maintain it, and this will be good enough for like most purposes, I would say. But then, of course, if you want to go down another order of magnitude to 300 milliseconds or whatever it is, then you want to do like all this bit-level magic, right? And then, of course, you talk about a very different level of complexity. As you saw, like this is probably not as easy to maintain. So it really depends on what you want to do. So let's say you build a database deep in the database kernel. This is what you want to do, and this is what people do. If you want to, win this coffee mug, well, this is then also what you want to do. Or And this is what I really, to me, it was like the most enjoyable outcome of this, I would say. If you want to get hired into the GraalVM team, because there was this guy, and I blank on the real name.
His name's Quan.
Quan, thank you so much. He goes by Mary Kitty.
He's from Vietnam.
From Vietnam, right. Yeah. And he did a very amazing SIMD trick for parsing the numbers. He came kind of out of nowhere, and boom, he had like this super amazing trick. And as I learned just the other day, he actually now works on the GraalVM compiler team to, make the compiler faster, make sure it does all the SIMD stuff correctly and fast. So really cool to see
because basically the next thing Graal wants to do is actually support this vector API as well. And Thomas is actually predicting that other entries that are currently not winning, if Graal gets updated, will be better than his own solution,
right. So
which is really cool.
People are still busy with it, although it has finished like a month ago. But then, yes, so it was meant for the Java community, right? So this was, well, what I could measure, what I could evaluate. But then people did it in all sorts of other languages, so even things like COBOL, of course, like Rust and C and .NET and so on. So all kinds of languages, but then also tools like databases and Snowflake. They did the 1 trillion row challenge, because for Snowflake, 1 billion rows is not enough. And well, as I mentioned, I could not measure all those things, right? It just wouldn't have been possible in terms of the effort. But we had this show and tell section, so you can go to the QR code, and there, people were free to share all their implementations other than Java, and it's still actually people still post there and put comments there, so it's still going on, and it's very inspiring to see. So I would say this repo is like really a invaluable resource for that kind of stuff. Few statistics. So overall, like 587 pull requests, 164 submissions, tons of discussions, 61 discussions in the show and tell. This Stargazer stat, actually, it's outdated by now. It's like 6K stars, so twice as much. And my favorite stat, 187 lines of comment in Alexei Shipilev's implementation. So definitely check out this one, because he goes to really great length to explain what he did and why he did it. Lessons learned? Well, first of all, you want to be precise with your rules, right? So the community came together and helped with creating this TCK. So we refined it later on. If I wanted to do this again, I would probably try and have a TCK from the get-go. Also, I would, and it happened here, right? So we came together as a community, so I would like to have this from the get-go. And it should be automated, right? So instead of me having to go for every pull request and run it manually, well, ideally it would be like a custom GitHub Actions runner, which runs on that machine, so people could kind of self-submit their entries. We would run the TCK, then we would run the performance benchmark, and then everything, like the leaderboard, would be automatically
That's something that annoyed me very much, because you would only do the pull request once or twice or every 1 or 2 days.
Right.
And that was my only way to see if my code was actually faster, because I couldn't test it on my own machine. So my iteration was like 2 days.
Yes, exactly. So we would do that different if we ever do that again. We will see. So coming back to our beginning, well, I really think we could show you, doing that in like 1.5 seconds on 8 cores or 300 milliseconds on all the cores, Java isn't slow, right? So we really can go down to like amazing levels of performance there. And I think that's all we had for you. We have 2 minutes and 40 seconds for questions.
Short question.
Short question. Yes, yeah. Any questions? There's one, please.
Do I feel like I'm a C programmer? I felt like that during the contest, but no. Yeah. So if you start using these bit twiddling tricks, I really enjoy doing that. So I find it fun. So but I still rather do Java.
Right. And I only did the baseline implementation, like the streams code, so very Java-y, so I don't feel like a C programmer. But it really bugged me that I always was at the bottom of the leaderboard.
If you watch the deep dive back that we did on Tuesday, Thomas, he is a C programmer. Like he's doing the native compilation, then he takes the assembly, he goes through every instruction and CPU cycle. Like that's no longer Java. Sorry.
Any other questions?
Well then, thanks.
Thank you so much for joining by.
All systems are nominal. Initialize optimized Genesis sequence